Welcome to Lesson 5, Isotopes and Average Atomic Mass. Our lesson objectives: differentiate between atomic number, mass number, and average atomic mass, calculate the number of neutrons in an isotope, and calculate the average atomic mass for all isotopes of an element. So what is an isotope? Well, the word iso means same. So these are elements that have the same atomic number, that means the number of protons, but different mass. And that's a result of the fact that they have a different number of neutrons. So if you look at carbon 12 and carbon 14, for example, they both have the same atomic number, which makes them carbon, which is the number of protons. But they have a different mass number, mass of 12, mass of 14. That's a result of the fact that carbon 12 has 6 neutrons and carbon 14 has 8 neutrons. So 6 plus 6 gives me a mass of 12, and then 8 plus 6 gives me a mass of 14. And so we use isotope symbols to show the different mass numbers we have for the different isotopes. So we put the symbol in the center, like on our periodic table, the mass number in the upper left-hand corner, which is the protons plus the neutrons, and the atomic number, which is the number of protons, in the bottom left-hand corner. So let's see an example. So these are some of the common isotopes of hydrogen. We have protium, deuterium, and tritium. They all are hydrogen, so they all have the same number of protons. So if you look here in this diagram, they all have one proton, which makes them hydrogen. And what varies is the number of neutrons. We have no neutrons here, we have 1 neutron here, and we have 2 neutrons here. Recall that the mass of a proton and a neutron are the same, which is 1 AMU, or atomic mass unit. And so this has only one particle, one proton, so the mass is 1. This has a proton and a neutron, so 1 plus 1 gives me a mass of 2. And this has 1 proton and 2 neutrons, so 3 particles, a mass of 3. And then if you look at your symbols, how we actually signify them, we have a mass number of 1 for the protium, 2 for the deuterium, and 3 for the tritium. And the bottom number, the atomic number, the number of protons, stays exactly the same because that signifies the element. So for example, if you're asked to write the isotope symbol for oxygen 17, so first thing we do is look up oxygen. We see that the symbol is O. The atomic number for oxygen is going to be 8. That's the number of protons, and that goes in the bottom left-hand corner. And then the upper left-hand corner is going to be the mass number, which is 17 in this example, signifying that the mass number, protons plus neutrons, is 17. So then how many neutrons does it have? Well, you can take 17, the mass number, and subtract the atomic number, the number of protons, and you'll get the mass number. So 17 minus 8 gives us 9. So oxygen 17 has 9 neutrons. So let's check your understanding. Can you calculate the number of neutrons in an isotope? Now let's look at calculating the average atomic mass. So when we look at the periodic table, why isn't the atomic mass a whole number? Well, mass number, that's the number of protons plus neutrons, are going by number of particles. That's going to be a whole number. The atomic mass that's on the periodic table is a weighted average of all the naturally occurring isotopes that exist of that element and the relative abundances, meaning the amount of them. So for example, if I look at a sample of chlorine, about 67.49% of the atoms in that sample are going to have a mass of 35. So they're going to be the isotope chlorine with that mass of 35. About 32.51% of those atoms are going to have a mass of 37. So a higher majority of the atoms have this mass of 35. And so the weighted average, taking into the percentages that we have of them, for chlorine is going to be 35.453. So notice that more than half of the atoms have this mass of 35, and that's why the average is closer to 35 than it is to 37. But how do we exactly calculate out that average? Well, this is something you may be familiar with. When I calculate your grades for this course, it's a weighted average. 50% of your grade is based on exams, 10% is based on quizzes, 15% is based on labs, and 25% is based on the homework and the classwork. And so if all of your exam grades add up or have an average of 85, quizzes are 100, labs are 95, and homework and classwork is 80, I can't simply just add them up and divide by 4 like a normal average, because that would weight each category the same at 25%, and we don't want that. We want the exams to be weighted the most at 50% and quizzes the least at 10%. So what we do is we take the percentage of the category times the value. So 50 times 85, as I did here, plus the next one, 10 times 100 here, plus 15 times 95, as we did here, plus 25 times 80 here. Then I divide the whole thing by 100 to get these out of percent. And I get an average, or a weighted average, of 87. So that would be your average for the course. So let's see an example applied to our average atomic mass. So if I have two isotopes of boron, boron 10 and boron 11, the percentages that I have in a sample of boron are 19.78% have a mass of 10.013 AMU, meaning atomic mass unit, and about 80% or 80.22% of the isotopes have a mass of 11.009. So how do we get the weighted average? We're going to multiply the mass of each isotope by the percent abundance and then divide by 100. So we take this percent times the mass, as we did here, plus the next percent times the mass, as we did here, divide the whole thing by 100 to get these out of percent, and I get a weighted average of 10.82 AMU. So a good check is to look and see, does this number fall in between my lowest value and my largest value? And the answer is yes. It can never be less than your lowest value or greater than your highest value. Just like if we go back to our grades, your grade for the course cannot be higher than your highest or lower than your lowest. Now, also looking at your average that you calculate out, if you look at this chart here, if the vast majority of my isotopes have this one mass, that means the weighted average is going to be very close to this mass and not as close to the one that is the least percentage. So if about 80% has a mass of 11, it makes sense that my weighted average is very close to 11 as compared to the 10. Let's see another example. Determine the weighted atomic mass for potassium. So we have potassium 39 and potassium 41. So about 93.1% of the isotopes have a mass of 38.964, and 6.88% has a mass of 40.962. So to get our weighted average, we're going to multiply the percent abundance by the mass, as I did here, plus the next percent abundance times the mass, as I did here, divided by 100, and I get a weighted average of 39.10 AMU. Again, looking at our two values here, we notice that our weighted average falls in between these two values, which it should. If it doesn't fall in between those values, you know you made a mistake. And then if you look here, if the vast majority has a mass of approximately 39, it makes sense that our weighted average is much closer to 39 than it is to 40. So let's check your understanding. Can you calculate the average atomic mass for all isotopes of an element? At this point, you should be able to differentiate between atomic number, mass number, and average atomic mass, calculate the number of neutrons in an isotope, and calculate the average atomic mass for all isotopes of an element.